Hello everyone, welcome to this fourth session of Engineering Thermodynamics. So in our previous lecture, we had discussion on the state and properties of the system. Then later on, we have come up with definition of a few properties. So in this particular regard, I have categorized the properties into two different types: extensive and intensive. In case of extensive properties, they are having direct dependence on mass, and intensive properties are independent of mass. Okay. Then we have defined a specific type of property where we take the value of property per unit mass. So that particular type of property is called as specific property, and it's also an intensive property of the thermodynamic system. Okay. And after that, I have started giving you the formulation of different thermodynamic properties. So in this particular regard, we have actually discussed one property that particularly we have called as nothing but our specific volume, and we have seen that reciprocal of this specific volume is nothing but our density, and this property is nothing but an intensive property of the thermodynamic system. Okay. After that, what we have done, we have seen that for specific volume, when we are writing small v, definition is limit delta v approaches to delta v dash delta v divided by delta m, where delta v dash is nothing but it is the critical volume above which assumption of continuum is valid. Okay, so that is nothing but the value of delta v. So this we have seen in our previous lecture. Now we will continue our discussion further, and we will try to dig into few more properties. So one of the very important property that we need to measure while we are actually analyzing our thermodynamic system, that particular property is known as pressure of the system. Okay, and I think from your basic knowledge you already know the fundamental definition of the pressure. Pressure is nothing but refers to as the normal force per unit area. So if we are having any force which is acting because of the fluid medium. So for example, as I have told you yesterday, that if we are having a container and in that container some water is filled inside. So what will be happening if we draw the free body diagram of the water volume, we will be finding for that one that this weight of the water mg will be nothing but supported by some force, and that force will be nothing but equal to pressure into area. So that force on the water column is actually provided by this bottom surface of the fluid. Okay, so if we just now draw the free body diagram of this container, so what basically is happening in case of container, whatever this P into A I have drawn over here, which is acting in upward direction on the liquid column, that same amount of force this liquid column will be actually generating on this container surface. Okay, so here you can see this P into A. So the only thing you have to collect from this, that pressure always acts in a direction normal to the surface. Okay, so though pressure is having some direction, but that direction is always unique. Okay, so pressure has always unique direction, and what is that direction? That is nothing but it acts normal to the surface. Okay, so that is what we can recollect from the definition of pressure. Now if we have to define it in mathematical form, So I can write mathematical definition of pressure as P equal to nothing but limit delta A approaches to delta A dash. So like in specific volume, we were having delta V approaches to delta V dash. Similarly, over here, we will be having delta A approaches to delta A dash. Here, this delta A dash is nothing but having similarity to that of delta V dash. It means it is also corresponding to the scale above which our assumption of continuum is valid. Okay. So this limit, now we know that force pressure is nothing but force per unit area. So I can simply write it over here as delta F divided by delta A. Okay. So this is the mathematical definition of pressure. Now, when we are analyzing the thermodynamic system, what we want to do, we want to basically determine its properties. Okay. So once the system has reached to the state of thermodynamic equilibrium, at that given state, then we have to determine its properties in order to represent the characteristics of the system. Okay, so pressure is one of the very important property which can be easily measured. Okay, so there are certain properties which we cannot measure directly. So for obtaining these properties, what we do, we try to find the minimum number of properties required to specify the state of the system, and then with the help of these properties, we try to correlate others. Okay, so pressure is one of the very fundamental property, and it is very important property because it can be easily measured. So that's why pressure many times is employed for characterizing the state of the thermodynamic system. Okay, so now let us try to see that what are the devices we can employ for measurement of the pressure. Okay. So what I am doing, I am considering that I have a container, and let us consider that inside this container I have some gas. Okay, and let us consider that the pressure of the gas over here is P. Okay, now what I'll be doing, I'll be connecting one arrangement. Okay, so I'll be connecting one U-tube like arrangement over here, and I'll be employing this U-tube like arrangement for measurement of the pressure. Okay, so we already know, yesterday we have seen that if we are having fluid in some container, okay, if we have fluid in some container, what will be happening? If I consider H as height of the container, so what will be happening? We will be having value of pressure at this bottom as nothing but equal to what we have done. We have drawn the free body diagram. I have already told you that if, say, this is my container, for this container, what will be happening? This is my liquid column. So for this liquid column, if I consider H is height, so mg force will be acting in downward direction, and at the bottom, I'll be having some pressure force multiplied by cross-sectional area. Okay, so area of this cross-section of the liquid column. So if I do this balance, I'll be finding that P into A is equal to M into G. Now, if I can convert this mass in equal to density into volume, so I can write it as rho into volume, and volume I can write cross-sectional area into height. Okay, so this is now my entire replacement for mass times G. If I do, area will be cancelling out, and finally I'll be finding that pressure is nothing but equal to, if we are including the effect of gravitational acceleration and we are having sufficient height and density, then we will be having value of pressure as nothing but equal to rho into G into H. Okay, particularly in the direction of gravitational acceleration. Okay, so that is what, for example, if I have to determine value of pressure, so at this bottom point, this will be my value of pressure. Now, if I have to determine value of pressure at any intermediate height, say h by 2, then at this particular point, my value of pressure will be nothing but equal to rho G into h by 2. So it means pressure is having direct dependence with the height. So now we want to employ this principle only over here in order to devise some arrangement for measuring the value of pressure. Okay, so what we have done now, we have this gas over here, and we have connected one U-tube like device. So this type of device is particularly known as a manometer. Okay, so the device, U-tube like device, whatever I am plotting over here, this particular device is actually known as a manometer. Okay, so it is nothing but a mechanical arrangement which is used to determine the pressure. So what I have considered, that we are having a container, and inside this container I have some gas. Okay, now what I'll be doing, inside this manometric tube I'll be taking some liquid. Okay, so inside this manometric tube, what I have done, I have taken some liquid. So some liquid I have considered over here. Okay, this particular liquid which we use inside this device, this liquid is called as manometric fluid. Okay, so this liquid is called as manometric fluid. So generally we use water, alcohols, mercury as different manometric fluid while we are employing manometer for measurement of the pressure, depending upon the magnitude of the pressure and depending upon the type of the fluid whatever we are employing for measurement of the pressure, and sometimes also depends upon the orientation of the manometer also. Okay, so over here we will try to see very simple manometric arrangement, single U-tube type arrangement for measurement of the pressure. So what I have done, one end of this tube I have over here connected to the container of the gas where I want to measure the pressure, and other end of this container is nothing but open to atmosphere. Okay, so here we are having our surroundings only, atmosphere. So it means at this particular end we will be having P atmospheric pressure which will be acting over here. Okay, now what we know that in the vertical direction, if we are having a difference of elevation, that is nothing but represents the hydrostatic pressure. Okay, so that is what we will now try to do. Now let us consider that whatever the manometric fluid I have considered over here, so this manometric liquid, for this let us consider density is rho m. So rho m is nothing but the density of the manometric fluid. And let us consider whatever this gas I have taken inside the container, it is having pressure P and density rho. Okay, and now what we are doing, because I have told you we will be having majority of the time liquid as manometric fluid. So because of that, density of this gas will be very small in comparison to the density of the liquid. So I can take one assumption over here that my density of manometric fluid is very large in comparison to that of the density of the gas. This is one assumption I can take. Okay, now if I just take this point as my reference point, so why I am taking this point as my reference point, because below this point in both the branches of the U-tube I have same fluid. So here also I have rho m as density, here also I have rho m as density. So whatever this height I will be having, say if I call this height as nothing but h dash, so what is basically happening, for this h dash height in the left branch of the manometer also I have rho m g h dash pressure, and in the right branch also I have rho m g h dash pressure. So what will be happening, both these pressures will be actually equal, so these will be cancelling out. That's why I can set the reference at this particular point. Okay, so here I have set the reference. Now let us consider with this reference point the height or the rise of the manometric fluid inside this tube is nothing but equal to, say, h. Okay, and now if I call the left branch point as A and reference point corresponding to right branch as, say, my B. Okay, now what I have to do, if I have to find out the value of pressure at point B, so what will be the value of pressure at point B? We can clearly see B point is at h height below the atmosphere. So that's why rho m into gh, will be the pressure at point B. Apart from that, atmospheric pressure is also acting from the top. So that's why pressure at point B will be equal to nothing but rho m times G into H, and we will be having plus P ATM also. Okay. So let me once again explain this point. So this is our point B, and at point B, what is basically happening? We are having this H height of manometric fluid. So that H height of manometric fluid is giving me pressure of rho mg into H, and at the same point of time, this other end of the tube is actually open to ambient. So because of that, atmospheric pressure is also acting over here. So PATM will also come into picture. So finally, we will be finding that pressure at point B is nothing but PATM plus rho m into G into H. Now, as I have told you that below this reference line, on the both the ends of this tube, we are having same height H dash. So that's why this pressure will be cancelling out. So I can simply say that my pressure at point A will be exactly equal to pressure at point B. Okay. So this is another condition, that pressure at point A is exactly equal to pressure at point B. Okay. Now what will be happening, for whatever the height H, we have manometric fluid on the right column. For the same height H, we have now this gas over here. So here we have this gas. So that's why in this particular region, we will be having some pressure equal to that of density of gas G into H. Okay, rho G into H. But we have already taken the assumption that density of manometric fluid is very large in comparison to the density of gas. So that's why value of this rho GH on the left hand branch will be almost equal to 0. Okay, so we are considering this value as very, very small, approaching to 0. Okay, so because of that, what will be happening now? We can consider that from this particular gaseous container, the container which is filled with the gas, from this container, whatever the pressure we are having inside this container, same pressure is actually acting over this point A. So at this point, the container pressure is only acting. Okay. So now PA is already equal to PB, and that because of the negligible density of the gas, I have made it equal to nothing but pressure of the gas chamber. Okay. So from here, I can simply write that pressure of the gas chamber is nothing but equal to rho mg into H plus P atmosphere. Okay. So let me write this equation on the next paper slide. So what I have done, I have told that P is nothing but equal to P atmospheric plus rho GH. Okay. Now, if I take the difference between the two pressures, in that case, what will be happening? P minus P atmospheric will be equal to, so this is rho m actually. So if I take the difference P minus P atmospheric, so P minus P atmospheric will be equal to nothing but rho m G into H. Okay. So now in this particular first case, when we are measuring the value of pressure, here we are measuring the value of pressure with reference to the absolute vacuum. So that's why this value of gas pressure will be nothing but in our absolute scale. Okay, so this is our absolute pressure. And when we are measuring the pressure of the container with reference to atmospheric pressure, so this particular value will be nothing but in our, so this rho GH value, nothing but it represents the gauge pressure. Okay. So let me now first give you the more detailed understanding that what is the difference between absolute pressure and gauge pressure. Okay. So how we can do, let me plot the reference line for the pressure. Let us consider along this ordinate, I have different values of pressure. Okay. And let us consider that this line over here is nothing but whatever this line I am drawing, say this line is nothing but corresponding to 1 atmospheric pressure. So if this is 1 atm, this is nothing but our P atm. Okay, and value of P atm, we know that nothing but 101.325 kilopascals. Okay, so this is my line corresponding to atmospheric pressure, and this bottommost line is corresponding to the zero pressure. Okay, so pressure will be zero because we know that pressure is something which is caused by the collisions between the molecules. Okay, so pressure will be equal to zero when we are not having any medium present. Okay, so where we are having absolute vacuum, if we are having absolute vacuum inside an container, inside a container, corresponding to that we will be having actually zero pressure. Okay, so what I am saying, corresponding to this bottom line, if I consider we have the value of pressure equal to zero, it means this bottom line is nothing but referring to the physical state of absolute vacuum. We are not having any material medium present inside the container where we want to measure the pressure. Okay, now what will be happening, say if I have employed some manometric device or any other device for measurement of the pressure, and I have found some value of pressure over here. Say this is my value of pressure. Okay, so this is some value of pressure which I have obtained. Now if this is my value of pressure P, I am writing it as a PA. So if I measure this value of pressure with reference to zero, if I measure this value of pressure with reference to absolute zero, then this particular pressure is actually called as absolute pressure. Okay, so from here now you can see, and another thing, if I consider this 1 atmospheric as my reference pressure, and if I measure the same value of this pressure, if I measure the pressure at the same value, but now I am taking my reference as nothing but this atmospheric line, so corresponding to that, whatever the value of pressure I will be getting, that is called as our gauge pressure. Okay, so if any pressure value we measure with reference to the absolute vacuum, it is called as absolute pressure. If any pressure value we measure with reference to, please, some of you is talking. Okay, please mute your microphone. I think Varinder Singh is talking. Please, Varinder, please keep your microphone muted. So what I was telling, that if I measure the pressure with reference to absolute vacuum, in that case, what will be happening? Our value of pressure will be absolute. And if I measure the pressure with reference to atmospheric pressure, so this will be my value of pressure. Okay, because if I take the reference atmospheric only, so my range measurement will be only up to this value. So because of that, what will be happening? We will be having only gauge pressure. Okay, so because of the gauge pressure, what will be happening? Just let me put this on mute. Okay, so because of the gauge pressure, now what will be happening? If you try to find out the relationship in between absolute pressure and gauge pressure, you can clearly see this entire is our absolute. This over here is nothing but our gauge pressure, and from this point to this point is our P atmospheric pressure. Okay, so if I have to relate the relationship in between absolute and gauge, I can clearly say that my P in absolute is nothing but equal to pressure in gauge plus P atmospheric. Okay, so this is the overall idea. And if I don't include the atmospheric pressure, it means if I consider atmospheric pressure equal to 0, and corresponding to that, if I measure the pressure, then whatever value I'll be getting, that is called as nothing but our gauge pressure. Okay, so majority of the pressure measurement devices, whatever we construct, these basically gives us only gauge pressure. Why? Because these devices consider the situation corresponding to atmosphere as the balanced condition. Okay, so at the balanced condition they give zero reading. For example, if I take a manometer, so what will be happening if both the ends of manometer are open to ambient? We will be finding that the level of manometer in both the tubes will be equal to 0. Okay, so it means if we only see the difference of height from the manometer, this h, so whatever value rho gh I'll be getting, this rho gh value will be nothing but my gauge pressure. Okay, so if I have to convert it into absolute, then I have to add atmospheric pressure. Okay, so that is the idea when we are having, so that is the relationship in between the absolute pressure and the gauge pressure when we are having actually measurement of positive pressure. Positive pressure means when our pressure, what we want to measure, that is greater than our atmospheric pressure. Okay, now we may have another situation where we want to measure the pressure at some point which is actually below atmospheric pressure. So that now let us try to see in the next slide. So here this line I have considered as 1 atm. This is my pressure over here. Okay, and what I want to do, say now positive pressure, I have already told you, if our pressure is above atmospheric, that will be our positive pressure, and if our pressure is below atmospheric, that we normally call as negative pressure, or sometimes we also call as vacuum. Okay, so if I want to say obtain the value, if I am getting the value at this particular location, so this is the value of pressure which I am getting. So this will be my nothing but, if I measure with reference to absolute vacuum, this will be my value, absolute value of pressure, and this absolute value of pressure, because it will be less than 1 atmospheric. Okay, so that's why this is nothing but representing our vacuum pressure. Okay, now if same value I have to measure with reference to the 1 atmospheric condition, then what I'll be finding? I'll be finding the measurement in negative direction. Okay, so whatever this I have represented over here, this is nothing but my absolute value in vacuum, and whatever this green line I am representing, this over here is nothing but my gauge pressure, because now my reference point is 1 atmospheric. So I am going from 1 atmospheric in the negative direction, so this will be a negative pressure and it will be my gauge pressure. Okay, and now we already know that if I measure with reference to absolute, so this is my 1 atmospheric pressure, or I should write it as P atmospheric line. So I can clearly write from here that my pressure, absolute pressure in vacuum is nothing but equal to P atm. So this much minus P vacuum in gauge. So minus P gauge vacuum. Okay. So that is the relationship in between absolute pressure and gauge pressure when we are having actually measurement of the negative pressure values. Okay. So I think already I have told you the different reference points for measurement of the this pressure, and at the same point of time I have also explained you about the device mechanical arrangement which is used for measurement of the pressure. Okay, now let us try to see slight modification of manometer. So slight modification of manometer is known as barometer, and barometer is a device that is used for measurement of the atmospheric pressure. So that's why many times atmospheric pressure is also known as barometric pressure. Okay, so what we do in case of barometer, we take some container. So this is say some my tank, and inside this tank we will be taking some manometric fluid. Okay, so here we will be having some manometric fluid, and then we will be having one inverted tube over here. Okay, so we'll be having some inverted tube, and now what will be happening? This manometric fluid, if you can clearly see from here that if this tank is open to atmosphere, then atmospheric pressure will be acting at this point. So here we will be having atmospheric pressure which will be acting over here. So because of that, this manometric fluid will be rising in the tube. Okay, so this manometric fluid will be rising in the tube. Say H is the height up to which this manometric fluid has rised inside this particular tube. So now what will be happening? Here I'll be having some space. So this space we try to consider as nothing but our absolute vacuum. We consider that we are not having any medium over here. So why we can take the assumption of absolute vacuum over here? Because many of the time when we employ barometer for measurement of the pressure, what we try to do, we actually use mercury as our manometric fluid. Okay, so when we use mercury, what will be happening in this particular tube? While liquid mercury will be rising, there may be evaporation of mercury, and we may find small vapors of mercury over here. Okay, so now we know that the vapor pressure of mercury is very small at the ambient temperature condition. So because of that, we can actually neglect this vapor pressure, whatever will be acting on the upside of this liquid column. Okay, so because of that, now if we draw the FBD of the liquid column inside this particular tube, we will be having weight of liquid column in downward direction, and from the bottom we will be having nothing but our atmospheric pressure which is acting. So that's why we can clearly say that atmospheric pressure is nothing but equal to rho g into H. Okay, now while we employ the barometer, so now one may get confused that what tube size we should consider. This inverted tube, what should be the size of this tube? Okay, so we may have different situations. For example, if I take a smaller tube, in another case I may take a tube of larger diameter, in another case I may take a tube say of some another cross section. So in first case, say if my cross sectional area is A1, in second case if my say cross sectional area is A2, and in third case if my cross sectional area is A3. Okay, so now what will be happening, because we are having over here the weight of liquid balanced. So if area, because while we will be drawing the free body diagram for calculation of volume, whatever has been raised in this particular tube, for that we will be having area into height, and for pressure we will be having force into area. So both areas will be cancelling. So we can use any size of the tube while we are actually devising barometer. Okay, the only limitation will be coming that size of the tube should not be of capillary dimension. Why capillary dimension it should not be? Otherwise what will be happening, if we are having size of tube very small, where surface tension effects are becoming prominent, under this condition what will be happening, we will be having actually rise of liquid caused due to the surface tension effect also. Okay, so there we will not be accurately able to measure the value of the pressure. Okay, so like this is all about the pressure. With this I would like to conclude our discussion on pressure. Now let us talk about another thermodynamic property which is called as temperature. Okay, so now our next thermodynamic property, temperature, is also very important property because it can be easily measured. Okay, so you might have seen for measurement of the temperature, many times we use thermometer. So these thermometers are nothing but mercury in glass thermometers, and their expansion of the mercury takes place once it reaches thermal equilibrium with the system for which we want to measure the temperature. Okay, so temperature is something, I think it's a very common term which all of us generally can express by just feeling the degree of hotness or coldness of some system if we just touch that particular system. So for example, when we touch a hot metallic rod, we generally say, so our we generally perceive that okay, it is of high temperature. And if whether we are touching some block of ice, generally we say it is of low temperature. So it means in some general sense, temperature is something which represents the degree of hotness or coldness of some substance, okay, whatever we are actually analyzing. Okay, but what basically happens, from our senses we cannot exactly obtain the value of the temperature. So that's why we should have some direct measure of the temperature, where we will be having certain properties which will be changing with the temperature in an predictable manner. Okay, so what we have generally seen with temperature, one of the good thing which we have seen is that if we are having different type of systems, for example, if I take two identical copper blocks, so say this is my copper block 1 and this is my copper block 2. Now I am using term identical for these two. So it means their material, size, etc. everything is same. Okay. Now initially what I have done, I have actually kept this copper block at some high temperature. So how we have known that its temperature is high? So what we can do, we can use some thermometer over here, and with the help of thermometer actually we can check that what is its temperature. Okay, so that is when we are knowing already about the thermometer. If we are not knowing about the thermometer, so at that time what I can do, I can actually measure the initial resistance of this copper block. Say R1 is my initial resistance of the first copper block. Okay, so R1 I am calling as nothing but resistance of this first copper block. And if I take once again the second copper block, and this second copper block I have actually maintained at low temperature. Okay, so I have cooled this copper block. Now if I say obtain the value of resistance corresponding to this situation as nothing but R2. Okay, so the initial condition is we are having this as high temperature, having resistance R1, and second we are having low temperature copper identical block having resistance R2. Now after that what I have done, I have actually made the physical contact in between the two. Okay, so once I'll be having a perfect contact between the two, what will be happening? There will be flow of heat from first block to second block. Okay, and we know that this flow of heat will be happening till we are getting same value of temperature. Okay, so finally after some time both will be having nothing but same value of temperature. Okay, so now corresponding to this same value of temperature, if I once again measure the resistance, let us consider for block 1 I have got resistance as R1 dash, and for block 2 I have got resistance as R2 dash. Okay, so obviously what will be happening, for the hot block resistance was low, so once this will be actually cooled, its resistance will be increased. So I can clearly say that my R1 will be less in comparison to R1 dash. And if I talk about R2, so in case of copper block, second copper block, what will be happening? Initially it was cold, so initially it was having high resistance. Now its resistance will be decreasing, so R2 will be greater than R2 dash. Okay, so that is something which we know from our fundamental understanding or temperature dependence of resistance. So now what we have done, that initially we were having different resistance, and then we made the thermal contact between the two blocks. Because of the thermal contact, these blocks have come to thermal equilibrium, and finally we have obtained the final value of the resistance for the two blocks. If blocks are identical, we will be finding that R1 dash is nothing but equal to R2 dash. Okay, now if you repeat this experiment for number of times, then irrespective of the number of times, you will be finding that every time when you are having the thermal contact between the two blocks and these are reaching to the thermal equilibrium, your value of resistance of both the blocks will be becoming same. Okay, so it means that we have got some property resistance which can be measured, and based on the resistance, as we are having some definite relationship in between the resistance and the temperature, so this resistance measurement we can employ for measurement of the measurement of the temperature. Okay, now this is like first scenario one.
Excuse me, sir.
Yeah, please. So I think it is better.
Sir, you told wrong, sir.
It is better if I take the questions later. Okay, so either in the doubt clearing session or after that session. Okay. So now what second scenario I want to take, say initially I have once again the same copper block 1, and then finally I have some another copper block 2. Okay, now these were at different temperatures. So what will be happening? Obviously we know that the inherent nature of the material is there, that we will be having some thermal expansion within the material. So if I measure the initial length of both the blocks as L1 and L2, and now if I measure the length after they are reaching to the thermal equilibrium, so let us consider that at thermal equilibrium their new length is nothing but L1 dash and L2 dash. Okay, so now what will be happening? Once this has reached the equilibrium, so this first block was hot and this was cold. So in case of first block, what will be happening? In case of first block, because its temperature is decreasing, so it means its length will be decreasing. So we will be having L1 as more in comparison to L1 dash, and if we talk about second block, we will be having L2 as less in comparison to L2 dash, because while exchanging the heat, the temperature of second block will be increasing, and once they are in thermal equilibrium, we can say that L1 dash is nothing but equal to L2 dash. Okay. Similarly, we may employ mercury in glass thermometer. So mercury in glass thermometer, what we do, we have some glass tube. Okay, and inside that glass tube we have very thin tube over here, and at the bottom we have some sensing element, and that particular sensing element is actually known as bulb, and inside this we put some fluid. Let us consider one of our fluid, commonly used fluid is nothing but mercury. So now what will be happening if we make the contact of this bulb with our system of unknown temperature for which I want to measure the value of temperature? What I can do, I can actually make this in contact with the system, and now because of the thermal equilibrium, there will be actually first transfer of heat because of the difference of temperature, and depending upon the thermal equilibrium between the two, we will be having actually after some time some constant height of mercury. Okay, so that constant height of mercury can be nothing but direct reflection of the change of temperature. Okay, so that is another point. Now these are the fundamental properties which may be employed for measurement of the temperature. But now comes the very important point, that how to define the scale of the temperature. Okay, so this is one very like important point. Like for pressure, I have told you that zero pressure will be corresponding to nothing but our absolute vacuum. Okay, so likewise, how we can define the scale for the temperature, that what will be the zero value of the temperature. Okay, so for this, what we can do, if we see in our different scales of measurements, whatever are available, you can see we are having degree Celsius as one of the scale of commonly used scale of temperature measurement in SI units. Okay, so this degree Celsius is normally used in SI units, and corresponding to degree Celsius, the absolute scale of temperature is Kelvin. Then in our engineering system of measurements, we are having actually Fahrenheit as scale of measurement. Okay, and then corresponding to that absolute scale of measurement is nothing but our Rankine scale, and we are having the relationship between the different scales of temperature measurement. But the important idea is, while these scales were developed, what were the basis for defining the zero value of the temperature? Okay, so let me just give you a brief background of the degree scale, temperature scale. So first, one point I would like to make you clear, why we use degree with C, because capital C is nothing but Coulomb, which is the unit of the charge. So that's why once the temperature scale was evolved, the symbol degree was put in association with C. Okay, so that's why we call temperature as nothing but degree Celsius. Now the idea is that while this degree scale and this Fahrenheit scale, these were developed during that time, scientists have taken ice point and steam point of water as the reference points. Okay, so this is one important criteria, that ice point and steam point of water, these were taken as reference point. Okay, because it was seen that under the atmospheric pressure condition, so this is also done at P atmospheric condition. So experiments were initially repeated, and it was found that under the atmospheric pressure condition, irrespective of the other parameters, if we just convert solid ice into liquid, it always happens at same value of some physical property. Okay, so that corresponding to that ice point, the value of temperature was specified as nothing but equal to 0 degree Celsius, and steam point is considered as the point at which our liquid water gets completely converted into vapor upon addition of the heat when we are having constant pressure maintained at atmospheric condition. Okay, so this point was given a value of 100 degree Celsius. So these were initially the reference point for designing the scale of for obtaining the scale of degree Celsius. Okay, and for Fahrenheit scale also only the ice point and steam point were taken, but these were given the value of 32 Fahrenheit was given the value of ice point, and 212 Fahrenheit was given the value of steam point. Okay, so the idea is that while Fahrenheit was designing the scale of the temperature, so he has actually initially considered as our body temperature as the reference scale, and he has given the value of 96 Fahrenheit to our body temperature, and corresponding to that 96 Fahrenheit value, he has tried to fit it that at what point this ice point corresponding to what range of the scale this ice point and steam point are fitting, and then the value of 32 and 212 were assigned, and this scale was actually designed. Okay, now whatever these scales we have got, whether this degree Celsius scale and Fahrenheit scale, both these scales are nothing but considered by taking some reference fluid. Okay, so what is the reference fluid? Reference fluid is nothing but our water. So it means these two scales are not of absolute nature. Okay, so when we talk about anything absolute, that should be applicable to all the mediums irrespective of the type of the fluid. Okay, so it is not of absolute nature. So then comes the idea of thermodynamic absolute temperature scale. So the idea comes of thermodynamic absolute temperature scale. So this particular idea we will be able to derive once we are actually going into the discussion of second law of thermodynamics. So at this particular moment, we will not be able to understand this concept. This will be coming into consideration after the understanding of second law of thermodynamics. But the only point I would like to mention that this thermodynamic absolute temperature scale, whatever we are having, it has been found that this scale, the Kelvin scale of temperature measurement, actually shows identical behavior to absolute thermodynamic temperature scale. So that's why Kelvin scale is actually considered as absolute scale of the temperature measurement. Okay. Then initially when we have started the idea of measurement of the temperature, and when we tried to obtain the absolute value of the temperature, we have actually gone or taken the help of ideal gas thermometer. Okay, so we have taken the help of ideal gas thermometer. So ideal gas thermometer is nothing but a constant volume temperature measurement device. It is constant volume temperature measurement. Okay, so what we do, we take a container, and inside this container we will be having some gas. Okay, and normally this gas we will be keeping at low pressures, because if we are keeping this gas at low pressures, then only it will be behaving as ideal gas. Okay, now this ideal gas will be having certain value of the temperature, and it is having fixed volume V. So this container where our gas is there, inside that we have nothing but our fixed volume V. Okay, so now we know that ideal gas equation is nothing but equal to PV equal to mRT. So R is some constant for a specific type of gas. Then M is also constant, because whatever the mass we have filled inside, that we are not changing. This is a closed system we have made, and this V is also constant because boundary of the container is fixed. So I can say that my pressure is directly proportional to temperature. So it means if I can measure the pressure, I can obtain the corresponding value of temperature and I can relate it. Okay, so for ideal gas temperature measurement device, what we do, for example, if I have a fluid for which I want to measure the pressure, what I'll be doing, I'll be putting this container inside that particular medium for which I want to measure the temperature. Now obviously what will be happening, this medium will be reaching in thermal equilibrium with the container, and inside this container we will be connecting a pressure gauge, and this pressure gauge will be actually giving me the value of pressure. As we have already seen that we are having linear relationship in between pressure and temperature under the assumptions we have considered. So I can say that my T is nothing but equal to A plus B times P, where A and B are some constants. Okay, so what we can do, initially while we will be taking this device, first we need to calibrate this device. So for the purpose of calibration, what we can do, we can consider this medium temperature as nothing but known. So initially we can take medium temperature as known, as we are having two constants involved in our equation. So that's why when we will be obtaining this medium temperature, so we have to take known medium temperature corresponding to two different points. Okay, so two different points. For example, one I can take as nothing but my ice point, and another I can take as my steam point. Now if I plot the relationship in between temperature and pressure, let us consider that at one point I have got the value, some experimental point over here, and corresponding to other situation I have got the experimental point somewhere over here. So now what I'll be doing, I'll be just joining both these two external points. Okay, and then with the help of these 2 points, actually I can determine the value of A and B. So now if I extend this line, extrapolate this line, so I'll be finding that at some point it will be actually reaching to the absolute value of the pressure. So where our value of absolute pressure is equal to 0, corresponding to that, we call that our temperature is also nothing but absolute temperature. So if I take this temperature, sorry, I have done it wrongly. So pressure will be on this side and temperature will be on this side. So what I am saying, that the point at which my pressure value is reaching to 0, corresponding to that, whatever value of my temperature is there, that I am calling as nothing but my 0 Kelvin, absolute value of temperature. Okay. So if you see in degree Celsius, so this value of this intercept is nothing but minus 273.15 degree Celsius. Okay. So from this point, it is clear that from the ideal gas thermometer, that when we are having absolute value of the temperature, absolute value of the pressure, it means when we are having perfect vacuum, corresponding to that we are having minus 273.15 degrees Celsius as our value in the degree Celsius scale. And because we are saying that our Kelvin scale is actually identical to that of absolute thermodynamic temperature scale, so because of that we will be finding that corresponding to this absolute value we will be having nothing but our 0 Kelvin pressure. Okay, so now let us consider that this line, whatever I have drawn, this is for say some gas 1 which is filled inside the container. Now if I change the gas from 1 to some 2, so for gas 2 also what will be happening, we will be finding that once we are extrapolating the line, it will be joining at same point only. Okay, so this is line for gas 2. So if I, apart from gas 2, if I go with any other combination of gases, I will be finding that this absolute point at which our absolute pressure is equal to 0, corresponding to that we will be finding every time same value of the temperature. Okay, so this is for some another gas 3. So now what I will do, I will stop at this point because it's time for your next lecture, and whatever your queries are there, that I'll try to take up in the doubt clearing session.